Welcome to our deep dive into quantum singularity theory.
QS, for short.
QS for short.
Yeah,
It really shakes things up
it does.
in terms of how we think about the universe, and I'm super excited to unpack it all with you.
Absolutely.
So, it's a theory that directly challenges
It really does.
the current reigning champion of particle physics.
Yes.
Quantum field theory.
That's right.
You know, QFT, I've always had trouble sort of wrapping my head around it. It says that everything is made of these continuous fields.
Right.
But what does that even mean?
So imagine like a perfectly calm ocean,
Okay.
right? That's your field.
All right.
And then picture like tiny ripples or waves
Okay.
spreading across that surface. Those are your particles, like electrons or photons.
Okay, I can kind of picture that.
Yeah.
So where does QS come in?
Right. So QS says,
How does it change this picture?
what if instead of this smooth, continuous ocean,
Okay.
reality is built from like tiny, invisible building blocks? Like imagine the universe is made of Lego bricks. Incredibly small Lego bricks.
Wow.
Yeah.
So instead of waves, we've got Legos.
Yeah, you can think of it that way.
So everything like particles, forces, even space and time are all made from these tiny singularities.
Yes, precisely. And that's where things get really interesting. You see in QS, even space-time itself isn't this fixed background stage. It's built from these singularities constantly interacting and evolving.
Okay, now my head is starting to spin a little bit.
Sure.
So if space-time is made of these tiny building blocks, does that mean it's not smooth and continuous,
That's right.
like we usually think of it?
It would have a kind of granular structure like pixels on a computer screen.
Oh, wow.
And this has huge implications, especially when we think about one of the biggest mysteries in physics,
Gravity.
gravity.
Right, quantum field theory just can't seem to explain how gravity works at the quantum level. It
Yeah.
runs into all these infinities.
It does.
And, which seems like a sign that something's not quite right.
Yeah, that's a great point, and it's where QS really shines. You see in QFT, they use this mathematical trick called renormalization
Right.
to deal with those pesky infinities.
Yeah.
But it always felt a bit like sweeping the problem under the rug, don't you think?
Yeah, it never sat quite right with me.
Yeah.
It feels like there should be a more elegant solution.
And that's what QS offers, because singularities are discrete.
Okay.
They inherently avoid infinities altogether. You can think of it like this.
Mm-hmm.
If you try to divide a Lego brick
Yeah.
into smaller and smaller pieces, you eventually reach the smallest possible unit. The brick itself, you can't go any further.
You can't divide a Lego anymore.
Exactly.
Yeah.
And this means that in QS, gravity emerges naturally from the interactions of these singularities
Wow.
without the need for any complicated mathematical workarounds.
So no renormalization.
No renormalization.
It's a much cleaner, more intuitive picture.
Exactly.
So what you're saying is that QS could potentially solve one of the biggest problems in physics, uniting quantum mechanics and general relativity.
It has that potential.
Yeah.
In fact, QS might be the key to finally understanding how gravity works at the most fundamental level. And what's even more exciting is that it resonates with other promising approaches to quantum gravity, like loop quantum gravity. But in QS, this discrete structure isn't just a mathematical tool. It's the very foundation of reality.
That's incredible. So we've talked about space-time, we've talked about gravity, but what about the particles themselves?
Right.
You mentioned earlier that in QS particles aren't these ripples in a field. So
Yeah.
what are they?
Well, remember those Lego blocks?
Yeah?
Imagine a large group of them arranged in a specific pattern.
Okay.
From a distance, this group might look like a single, solid object.
Right.
But up close, you can see that it's actually made of many individual blocks.
I'm following you.
Yeah.
So are you saying that in QS, particles are actually made up of groups of these singularities?
That's precisely it. Particles, as we observe them, are emergent phenomena. They arise from the collective behavior of many interacting singularities.
So it's not that particles don't exist, it's just that they're not the fundamental building blocks we thought they were.
Right. Think of it like a school of fish.
Okay.
From a distance, it looks like a single entity moving through the water. But up close, you can see that it's actually composed of many individual fish all swimming together in a coordinated way.
I like that analogy.
Yeah.
It makes this abstract idea a lot easier to grasp.
Good.
And this new way of thinking about particles could also shed light on one of the most puzzling aspects of quantum mechanics, wave function collapse.
Oh yeah, wave function collapse. That's the one where a particle's wave function suddenly collapses
Right.
into a definite state when it's measured, right?
Yeah, it's always seemed a bit mysterious.
It has.
Like, something magical is happening.
Exactly. But in QS, there's no need for magic. Remember how in QS particles are actually groups of singularities?
Right.
Well, the act of measuring a particle can be seen as disrupting the coherence of these singularities. It's like shaking up that school of fish, causing them to scatter.
So instead of this magical collapse, it's more like the group of singularities just loses its organized structure, and that's what makes it look like the particle has chosen a particular state.
Precisely.
Yeah.
And what's really exciting is that this view of particles isn't just some philosophical idea.
Mm-hmm.
It leads to concrete, testable predictions about the nature of particles in space-time that differ from what QFT predicts.
So if QS is right, we should be able to actually see these differences in experiments.
Absolutely.
Yeah.
And those experiments could revolutionize our understanding of the universe.
Well, I'm hooked. I can't wait to see what other surprises QS has in store for us. But before we go any further, I think it's time to take a quick break. We'll be right back to explore even more mind-blowing aspects of quantum singularity theory.
Stay tuned.
All right, so we've seen how QS reimagines particles.
Right.
But how does it tackle the even bigger puzzle of forces?
Yeah.
You know, in QFT, we have these force-carrying particles like photons for electromagnetism.
Right.
Where do they fit in this singularity picture?
That's another area where QS offers a beautifully elegant solution. You see, QS forces aren't carried by separate particles. Instead, they emerge directly from the interactions between the singularities themselves.
Wait, so no more force-carrying particles?
That's right.
How does that even work? I'm having trouble picturing it.
Think of it like this. Imagine you have two magnets. You know how they attract or repel each other?
Yeah.
Depending on how their poles are aligned.
Opposites attract, right?
It's a similar way. The different configurations and interactions between singularities in QS can give rise to the forces we experience. It all boils down to how these tiny building blocks are arranged and how they communicate with each other.
Okay, I see. So instead of needing a separate particle to carry the force, it's like the force is built into the very structure of space-time itself.
Exactly.
It's all about how these singularities are talking to each other.
Precisely. It's a much more unified and holistic view of forces compared to QFT.
This is all so fascinating, but I have to admit, part of me is still a little skeptical. I mean, it's such a radical departure from how we've traditionally thought about the universe.
It is.
How can we be sure that QS is actually correct?
That's a great question, and it's the hallmark of good science, to be skeptical. Any new theory, no matter how elegant or exciting, has to stand up to experimental scrutiny. It needs to make testable predictions that can be verified or falsified.
So what kinds of testable predictions does QS make? What should we be looking for if we want to prove or disprove this theory?
One of the most exciting predictions of QS is that space-time should have a discrete structure at incredibly small scales. Think of it like tiny pixels in a giant cosmic image.
So no more smooth, continuous space-time like QFT suggests.
Not according to QS, and the exciting thing is that we might be able to detect this graininess using incredibly sensitive instruments like gravitational wave detectors.
Okay.
These detectors are designed to pick up ripples in spacetime caused by massive events like black hole collisions.
But how could they detect these tiny pixels of space-time?
Well, if spacetime is discrete, those gravitational waves wouldn't propagate perfectly smoothly. There would be slight, almost imperceptible distortions or jitters caused by the granular structure of spacetime itself.
So it's like those gravitational waves would be slightly blurry?
Yes.
Or pixelated if QS is correct. That's amazing. It would be like seeing the individual atoms of spacetime itself.
Exactly, and finding those distortions would be a huge confirmation of QS.
Are there any other ways we could test this theory?
There are another area where QS could make its mark is in the search for exotic states of matter. You see, the collective behavior of singularities in QS could lead to brand new phases of matter that we haven't even imagined yet.
What do you mean by exotic states of matter?
Think of it like this. We're all familiar with the basic states of matter, like solids, liquids, and gases.
Right.
But under extreme conditions, matter can behave in completely different and unexpected ways.
Like how water can become ice or steam.
Yes, but think even more extreme than that. For example, in certain exotic states of matter, electrons can behave like they have no mass, leading to superconductivity, or particles can become entangled over long distances, leading to bizarre quantum phenomena.
So you're saying that QS could predict entirely new kinds of matter with properties we can't even dream of yet?
Absolutely, and if we find those materials, it would be another strong piece of evidence in favor of QS. It would mean that our understanding of the fundamental building blocks of the universe needs a serious update.
Wow, this is all so mind-blowing. It feels like we're on the verge of a whole new era of physics, and it's all thanks to this radical new way of thinking about reality.
It's an exciting time to be a physicist, that's for sure. We're peeling back the layers of reality and discovering that the universe is even more bizarre and wonderful than we ever imagined.
And that brings us to the biggest question of all.
Okay.
What are the implications of QS for our understanding of the universe and our place in it?
Well, if reality is ultimately built from these discrete, interconnected singularities, it raises some profound questions about the nature of existence itself. For example, if spacetime is emergent, does that mean that time itself is not fundamental? And if particles are just patterns of singularities, what does that say about the solidity of the world around us?
Those are some heavy questions. I think we're going to need a little more time to unpack all of this.
Yeah.
What do you say we take another quick break and come back to tackle these big philosophical questions?
Sounds like a plan. We'll be back soon to explore the deepest implications of quantum singularity theory.
All right, so we're back and ready to tackle some of the bigger questions that quantum singularity theory raises.
Okay.
We've talked about how QS could revolutionize physics.
Right.
But what about the bigger picture? How does it change the way we think about the universe and our place in it?
That's where things get really interesting. You see, if reality is ultimately built from these discrete, interconnected singularities, it challenges some of our most fundamental assumptions about existence. It's like we're looking at the universe through a whole new lens.
One thing I've been wondering about is time.
Okay.
In QS, space-time is emergent,
Right.
meaning it arises from the interactions of these singularities.
Right.
Does that mean that time itself isn't fundamental?
That's a question that physicists are still grappling with if QS is correct. It suggests that time as we experience it might be a consequence of how these singularities interact and evolve. Imagine those Lego blocks constantly connecting and disconnecting, forming complex patterns that shift and change over time. What we perceive as the flow of time could be a reflection of that dynamic process.
So time might not be this linear, absolute thing that we typically imagine it to be. It could be more fluid and interconnected, woven into the very fabric of space-time itself.
Exactly. And that has profound implications for our understanding of causality and the nature of reality. It's like the difference between looking at a still photograph and watching a movie. In the photograph, time is frozen, but in the movie, time unfolds, revealing a whole new dimension of complexity and change.
Wow, that's a powerful analogy. It makes me think about the particles we discussed earlier.
Yeah.
If particles are just patterns of singularities, does that mean that the world around us isn't as solid and permanent as we think it is?
That's another mind-bending consequence of QS. If particles are emergent, it suggests that the solidity of matter is an illusion, a macroscopic phenomenon that arises from the collective behavior of countless singularities. It's like a magic trick, where something appears solid and real, but it's actually built from something far more fundamental and dynamic.
So if we could zoom in close enough, we'd see that everything around us is constantly in flux, a swirling sea of interconnected singularities.
Yeah.
It's a far cry from the deterministic clockwork universe that classical physics envisioned.
Absolutely. QS paints a picture of a universe that is fundamentally uncertain and interconnected, where even the most basic building blocks are in a state of constant change and interaction. And this has implications not just for physics, but for our understanding of biology, consciousness, and even free will.
Now you're really pushing my brain to its limits. I mean, if everything boils down to these tiny singularities, does that mean that even our thoughts and feelings are somehow encoded in their interactions?
That's a question that philosophers and scientists are still debating. Some argue that QS provides a framework for understanding consciousness as an emergent phenomenon arising from the complex interplay of singularities in the brain. Others remain skeptical, pointing out that there's still a huge gap between our understanding of physics and our understanding of subjective experience.
So we're still a long way from having all the answers.
Yeah.
But QS certainly opens up a whole new realm of possibilities for understanding the universe and ourselves. It's like we've been given a new set of tools to explore the deepest mysteries of existence.
And that's the beauty of science. It's a never-ending journey of discovery, where every new insight leads to more questions and deeper explorations. QS might not have all the answers, but it gives us a new way of asking the questions, and that's what makes it so exciting.
Well, I don't know about you, but I'm feeling both inspired and a little overwhelmed by everything we've discussed today.
I can understand that.
It's a lot to process, but I think that's the hallmark of a truly great deep dive.
Absolutely.
Don't you think? It leaves you with more questions than answers,
Yeah.
but it also ignites a sense of wonder and curiosity about the universe and our place in it.
It does.
So as we wrap up this deep dive into quantum singularity theory, I want to leave you, our listener, with a final thought-provoking question. If reality is ultimately built from these discrete singularities, does that change our understanding of free will or consciousness? Could our thoughts, feelings, and choices somehow emerge from the complex dance of these quantum building blocks? It's a mind-boggling concept to ponder, and one that might just reshape our entire view of ourselves and the universe we inhabit.
Until next time, keep exploring.